Equation derivation. Now we're gonna learn that how to derive the main equation for the Z transform. What is the procedure to derive the equation for the Z transform? So let's do it. This is my plane with the imaginary axis and real axis. And here is my unit circle. This is the unit circle with the magnitude radius r equals to 1. This is my phase angle. What I'm doing, I'm deriving the equation for the Z transform. Before to go for the mathematical work, I just touched the graphical side. This is my real axis, r. R means real. And this is my imaginary axis. I means imaginary axis. It is a unit circle. It is a unit circle with a radius r equals to 1. If the radius of the circle is 1, then it is a unit circle. This is going to be my phase angle, which is indicated by the omega. Now according to the discrete Fourier transform, discrete Fourier transform equals to summation of x of n times e to the negative j omega n, with the n from negative infinity up to positive infinity. Look, this is the discrete Fourier transform of x of n. X of n is a source signal. So when you take the discrete Fourier transform, it equals to summation of x of n times e to the negative j omega n. This is the main equation for the Fourier transform. Remember, discrete Fourier transform and Z transform do the same job, but the only difference is that Z transform can be applied for both periodic and non-periodic signal. When it comes to the discrete Fourier transform, it is not able to apply it for both periodic and non-periodic. This is the basic equation for the discrete Fourier transform. Remember, it is in negative j omega n. You can also take iota, but it is better to take j with the omega. We took phase angle. Let me multiply both the sides by r to the negative n. Just multiply the left side by r to the negative n and the right side by r to the negative n. So I will have discrete Fourier transform of r to the negative n times x of n equals to summation of x of n times r to the negative n times e to the negative j omega n. Just multiply this term by r to the negative n and this one by the r to the negative n. Now, can I write this left term equals to r times e to the j omega to the whole n? Remember, I have negative n here and the same negative n here because I have negative sign here. So I can take negative n for both r times e to the negative j omega. Just take the power negative n for r times e to the j omega. So whether you write the expression in this way or in this form, it is absolutely one thing, because when you expand the power negative n, you will get back the same thing. Now let me let r times e to the j omega equals to z. Just make it equals to z. Plug in z for r times e to the j omega. So I will have summation of x of n times z to the negative n, which is the Z transform. Remember, this equation is my Z transform. That's what the Z transform looks like. When you go back and check the basic equation for the Z transform, it equals to summation of x of n times z to the negative n, where n starts from negative infinity up to positive infinity. That's what we got the Z transform. How we got Z transform? We got Z transform from the discrete Fourier transform. There I got my Z transform, which is x of z. It is the equation of the Z transform. But now look to the left side, I have r to the negative n here. Remember, if I put back z equals to r times e to the j omega. Remember, we let z equals to r times e to the j omega here, which is this. Put back r times e to the j omega for the z here. Now, if I plug in r equals to 1 here, r equals to 1 here, and r equals to 1 here, if I put back z equals to r times e to the j omega. What is r? R is the radius of the circle, remember. Why I put r equals to 1? Because the magnitude of that circle was 1, which was unit circle. If you remember, here, my r equals to 1, it is the radius of the circle, which is the unit circle. Therefore, I plugged in r equals to 1 here, and r equals to 1 here, which I can write discrete Fourier transform of x of n equals to summation of x of n times e to the negative j omega n, with the n from negative infinity up to positive infinity. Remember, 1 to the negative n is 1. So whatever power you take for the 1, ultimately it equals to 1. Therefore 1 to the negative n is 1. And 1 times e to the j omega is e to the j omega. Here 1 times e to the j omega is e to the j omega. But don't forget, I have negative n power here. So I can write e to the j omega to the negative n equals to e to the negative j omega n. Because I have power here and power here. So this negative n has a product with the j omega. So when you take the product of j omega with the negative n, you will get negative j omega n. So here I got the basic equation for the discrete Fourier transform. It is the equation for the discrete Fourier transform. It is the equation for the Z transform. Now, when you do comparison, we derived the Z transform equation from the discrete Fourier transform. It happened only when the radius is 1, which means that on a unit circle, discrete Fourier transform equals to the Z transform. The Z transform will be only discrete Fourier transform when we have the unit circle, when the radius is 1. At r equals to 1, we got the basic discrete Fourier transform equation. So I can write that x of z equals to discrete Fourier transform of r to the negative n times x of n. At r equals to 1, x of z equals to discrete Fourier transform of x of n. Remember, this is my x of z, which is the Z transform equation. It equals to discrete Fourier transform of r to the negative n into x of n. But then at r equals to 1, at radius r equals to 1, Z transform equals to discrete Fourier transform. When I plug in r equals to 1 here, 1 to the negative n will be 1. So we'll have discrete Fourier transform of x of n. Here the comparison is pretty clear. I repeat it again. That Z transform equals to the discrete Fourier transform when the radius r equals to 1, which means that on a unit circle, discrete Fourier transform equals to the Z transform. This is the basic relation between the discrete Fourier transform and the Z transform. And that's how we did some sort of derivation for the Z transform. And also some sort of comparison between the Z transform and the discrete Fourier transform.